Hello everyone, it's November 21st. Alright. I think we all have to, at least from my understanding, we all have to do this with segment tree. That's how I have to do it. And we'll also check the answer when we get it. But yeah, I think it has to be segment tree. Maybe it's not. Maybe I'm just wrong. Who knows? But from what I got yesterday, I feel like there's no way that we can get right, because yesterday we have concluded that if your x is big and your y is small, then it's not going to work. Yeah, because your smaller y we cannot pop. So what the small y has to be, a small y with a big x plus y has to be there. There's no other way. They have to be there. And we just have to handle it. Yeah, there's no other way. Yeah, we'll do segment tree. It's gonna be, a hassle, but yeah, it's alright. Alright, let's try this. Diagonal traversal. Given a 2D, return all elements in diagonal order as shown in below image. All the elements in diagonal. Ooh, ooh, this is interesting. This is very interesting. Ooh. Well, if I remember correctly, diagonal. Don't they have a certain quality to be on diagonal? Right? So, right, that's a 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Diagonal. The sum is the same. Okay, let's try this one. Oh my god. It doesn't matter, right? It doesn't matter. 1, 2, 3, 4, 5. Yeah, it doesn't matter. But then this is not what we want. Okay, this is not what we want. It's always gonna start from here, right? What I'm afraid of, is like something like this. Okay. We got a 1, 2, 3, 4, 5. How are we gonna go diagonal here? So it would be this, right? And then we'll this, and this. Oh, I think it's the same. 0, 0, 0, 1, 0, 2, 0, 3. Right? 1, 0, 1, 1, 1, 2. 2, 0, 2, 1. Yeah, it's still the same. So diagonal is always the same. So we just keep adding. So we know what is what. But then how do we order them? Well, the sum, right? The sum gets bigger. 0, 1, 2, 3, 4, 5. Right, this is the biggest. 6, right, is the biggest. Therefore, as we go through the first one, can we so the diagonal sum map. Yeah, we can do a map. Yeah, we can do a map. That's fine. I'm gonna do a map. Or we can do a list of list. No, we cannot do it. Let's just do a map. All right. Let's do a map, and then the sum is gonna be a list. So every time we encounter some, we put it in. Encounter something, we put it in. That does not sound right, because this has to go first. It's your x, right? It also depends on your x coordinate. Your not x, your the j or j. Your j goes first. Which means if I go this way, if I go vertically, then the first encounter is always going first. This is very interesting. Right? If I go vertically, this are the start of its corresponding diagonal. Right? And then this. And then once we go through everything, we go through this. Right? And then do it in order. This first, and then this, and then this, and then this. Huh. Okay. I think it works. Maybe there's a, there's always going to be a better way, but this is what I'm going to try now. All right. Again, no arrow keys. So first of all, I want to map as integer and then list integer. What do we call this? Diags. Okay. Then we're gonna go vertical. For vertical. It cannot even go vertical. Damn. You cannot go vertical. Because it doesn't have. Oh, well, if it doesn't have, then we just skip. Right? We just skip. That's okay. So, So nums.length. Int I j first column. Then when do we know it don't have any more? We'll worry about this one later. J smaller than what? J smaller than what? Exactly, J smaller than what? We don't know. Well, I think we need another thing called a boolean. More J's. Yeah, we set to true. And then we say more J's. J++. Okay. And then for int I equal to 0, I smaller than nums.length size I++. Okay. Right. Then what? Then we are going to say, more J's. Num j changed. Num j changed. We might as well just do a while loop. Seriously, I think a while loop might be easier to deal with. Say the j equal to 1 equal to 0, right? And then this is going to be while true. Okay. And Boolean has encounter false. Okay. And then for each one we say if nums I, no, that's not right. Nums.get I. Nums.get I dot size is larger than j. Right? Then diax put if absent I plus j, new list, new array list, right? And then diax dot get I plus j dot add nums dot get I dot get j, and has encounter equal to true. Right. So as we go through this, we say if not has encounter, then we'll break. And then j++. Right, we'll go through the top to bottom. Right, go through everything. If the length is larger than j, then we have nums.get I.get j. And we'll add it. And then j encounter, and then j++. Then we go back up, go back up, go back up. Once everything is done, okay? Once everything is done, we need to return an int. How do we know the total number? We don't, unless we compute. Or we to array. Yeah. We say list integer rest list equal to new array list. Okay. Then for we need to sort. List. Wait, hold a second. Yeah, list integer keys equals to diax dot key set. It's a set. So we say new array list. I probably can put this one inside. And then collections dot sort keys. Okay, for int key of keys. Res list dot add all diax dot get key. We'll return res list dot to array. That's not right. Shoot. It's okay. So we say int res equal to new int res list dot size for int I is 0I smaller than res list dot size plus res I res list dot get I. Ugh, that's not right. 3K. Is that right? Is it fast? No. Will it time out? What? Oh, we're visiting this over and over again. Oh, dirt. Yeah. We shouldn't. Yeah. All right. Damn. So what do you say? Well, we'll have to go row by row. Row by row, then we need to sort. Yeah, I guess it's okay, right? Okay, so this is not right, but it's fine. Actually, this part is actually gonna be easier. Okay, we'll go to the front. Nope, that's not gonna work. I'm gonna do all the way to 12. Delete this. And for int I equal to 0, I smaller than the length size I plus plus. Okay, for int j equal to 0, j smaller than nums dot get I size j plus plus. Ix dot put if absent I plus j, new array list. Ix dot get I plus j dot add nums dot get I get j. Okay. Rest list. We get a key, sort the keys. Then we just do one more ix dot get key. We just sorted collections dot sort. That's not right. That's not right. Oh, we just go right to left. Yeah, we just go right to left. So for each k, we shall say for int I equal to 0, no. I to ix dot get key dot size minus 1. I logic is 0, I minus minus. Because this is the last one in this. Right? So this, so when we go this is the first, second, so we should go with this one first. Yeah, that's fine. Okay, so for this, we're gonna say res list dot add ix dot get key get I. All right, let's see if this one works. No, go back. Back to front. Yeah, I was just trying to. No, I think this is the solution. This is the way. This is the way to go. Yeah, but it's slow, so yeah, gotta figure out why. I mean, because you use hash map. I wonder if we can avoid using a hash map. All the cells on the same diagonal has the identical I plus j sum. Right, traverse nums row by row and put all the values of the same diagonal in a list. Then grab the list from the smallest I plus j sum to the largest. I'll call it O&M, right? What? It's slow. Let's see. Why is it slow? Because you use this. But I don't know. I mean, you can do. Yeah, I guess so. Because we know. What's the largest? Well, the row, the largest, the 10 to the 5th. So 10 to the 5th plus 10 to the 5th. Right? That's the largest that you can get. So 2 times 10 to the 5th. But it might take a lot of memory. But you don't have the sort. I don't know. And use a map. They count n. While groups don't contain keys. I see. They'll avoid. They just go through the. Yeah, I think it's all right. But this breadth first search, that's interesting. Huh. Huh. That's true. Row plus 1, column. Oh. I see. Everybody can visit to the right. We don't need to consider the square down if it's at the front. Everybody else. Holy crap. Great. It's a great solution. This is the BFS solution from the official. The main idea is that if we consider each cell in nums as a node, the next diagonal values are current nodes down and right neighbors. Thus, if we BFS from the top left, each round of BFS, right? Each round of BFS constitutes each round constitutes the current diagonal. Not the current, constitutes a diagonal in order. The solution also uses a trick to avoid the usage of a hash set to avoid duplicates. If a node is on the left edge, we consider its down and right neighbors. Otherwise, we only consider its right neighbor. And this is OMN as well. Alright. So we don't need any of this. So I think we can delete all of them. So what we need to do is have a list of integer. This is still exist. Hash list. No, res list. Right. And then we need a queue. We're gonna do an actual queue. Which is a deck. Array deck. Okay. And then we're gonna push. No, it's not an integer. This is int. Okay. And then q.add new int 0, 0. Oh, what the hell? Alright, 0, 0, and push 0, 0 in. And the res list dot add nums dot get 0 dot get 0. That's the original. That's not right. That's not right. I don't think, no, this is not right. I'll just say while not q dot is empty. Okay. For int I equal to 0 smaller than q. Size and I plus plus. Okay. Tuple pull. Right. So we pulled it out. This is what we are going to add nums.get top 0 .get top 1. What happened? May produce null. I won't. Maybe we're gonna do 2. No, that's not gonna work. It's not gonna work. Anyway, so yeah, this one does, right? And then we need to say if if top 1 is equal to 0 and top 0 plus 1, so we go down, right? We go down 1. Top 0 plus 1 is smaller than nums.length dot size. If that's the case, then q.add new int 0 and top 0 plus 1. And then if top 0 plus 1, okay, just to your right, is smaller than nums.get top 0 dot size. Right, so we have more than q dot add new int top that's not right. This is not right. This is a 1. Then when add, the new is 0 top 1 plus 1. All right, and then blah blah blah. Once we're done, I say int res new int restless dot size I smaller than res size. All right, let's see. Oh, pending. So long. Alright, I think this is not going to work. Let me refresh it. Index out of bound. That's interesting. Huh. How? Oh, I see. This is wrong. Type 1 is 0. Yeah. Yep. That's the thing. Good solution. Faster, better. Okie dokie. That's that. Done. All right. You want to do this? No, I do not. But at least we have to try. If it doesn't work, then it's a different story. Oh, we can do. No. No. Oh, this line number. Huh. Interesting. Hold on. Sublime text line number relative. Oh, I cannot do it? There it is. All right, hold on. Yank. Come here. Paste. And we'll go false. Change to true. Holy crap. That's the stuff, man. That's the stuff. Yeah. Awesome. Oh, I can also choose to solve these, but it's okay. All right, it's gonna take a lot of effort for this one to be done. So what do you want to do first? Well, I think the first thing we can do is seg tree. So what do we need for segment tree? What we need is, n, the size, right? We need a size. That's about it. Then we say self n equal to n. And then what do we have? We need an array. Self dot tree. What is this? I think it's 2 to the something power. And that power is math.log n divided by math.log 2 and then we'll say math.ceiling of this okay, ceiling of this, and then plus 1. This is a guarantee will work. Okay, so I have the tree, we have this. Okay, so we have first one, update. So when we do update, what we want is index. Oh, so we have 2 types of index, right? We have the range index and the actual index. Start range and query start query. So it's index and the value. All right, this is what we do. Don't return anything. And then we also have a query. Right, query, we have a query left, query right. This one needs to return an integer. All right. We have the underscore update. So what we need is range left, range right. Okay. Range left, range right. Query left, query right. I mean, it's not query left, it's just index. It's update, we update a single value. What else? And a node. It was gonna return an integer. Really? Return integer? No, we don't have to return an integer. This is the update, right? So basically we say index is inside the range left and range right. I'm going to update that. So if range left is equal to range right is equal to index, right? This definitely happens. Then self.tree node, okay, or equal to value. Oh, where's value? Right, then we have that. Return. Otherwise, mid is this plus this. 2. Okay, so I have the mid. Then we say if index is smaller or equal to mid, then we'll call update range left mid index node times 2 plus 1. This is the left child value. Else self dot update mid plus 1. Range right index node times 2 plus 2 val. Okay, once we're done, self dot tree node equals to maximum self dot tree node children. That's why, because it's a max sec tree. Oh, don't use this. Come on, you can jump. Max sec tree. Right, jump down. That's it. Yeah, the maximum on the left, the maximum on the right, and then we put it back together. Okay, now we're gonna do query. Query is the same thing. We have that, but now we have query left, query right, have a node. We don't have a value. Just return an integer. Okay. So how is this? Well, we have query left, query right, and we have range left, and range right. So if range left is equal to query left and range right equal to query right, I don't think you need to do this. We return self.tree node. Okay. Else. So the query right, query left, query right, and we'll say if everybody is positive, right? Yeah, so we can return 0. So if query left is larger than range right, or query right is smaller than range left, these will return 0. Okay. Then what? Then we have overlap, right? Then we have overlap. So we go to mid is equal to range left plus range right. Then what? Oh, have more things. Because it's the mid, right? So what we want to do is, now I don't like how this one is going. I don't like how this one is going. Hold on, I don't like this. I'm gonna analyze here. So we have a mid, right? So for the next round, we have the ranges here, query ranges here, right? Then I have a mid. So if query right is smaller or equal to mid, Okay, so everybody's on the left hand side. So query right is smaller equal to mid. Then we'll do self.query range left mid query left query right no times 2 plus 1. I mean, basically we'll return this. Okay, if query left, query right is smaller, right? And if query left is larger than mid, then everybody's on the right hand side. So self.query mid plus 1 range right QL QR no times 2 plus 2. Okay, otherwise query right is larger than mid and query left is smaller equal to. So in this case we shall return max two things. Okay, so it's gonna be self.query range left to mid query left mid node times 2 plus 1, right? That's 1 because mid is in between query left and range right. So we got a mid, yeah, and then self.query mid plus 1 range right mid plus 1 query right node times 2 plus 2. So that is query. All right, now we have to write update. So when call self.update, we start from 0, range left, range right is self.n minus 1. Index is index. Node is 0. Value is val. Done. Query will return self.query range left, range right, query left, query right, node. Okay, so that is my segment tree. You might want to test this. Like seriously, you might want to test this. We can test this. We can say, you know, yeah, for n in nums1, for I n in enumerate nums1. Well, before that, max sec tree equal to new max sec tree. New max sec tree. N. What's the n? The range. Is that the count? Right, 4. Okay. So with that, we can say max this dot update. Update what? Index. Index is I, and the value is n. Okay. Then we can just print query. You know, let's say 0 0. Yank, paste, paste, paste. Okay, so let's try a few more. 0 to, you know, to 2. Maybe 1 to 2. 1, 2 to 3. Oh. Okay. And delete that. Tests. Yeah, I might as well just delete both tests. So we have 4, 3, 1, 2, 2, 4, 9, 5. Query 1, 3, 2, 5. Second test 3, 2, 5, 2, 3, 4. I don't know, I think these are just good practice for my Vim. If there's anything that I can practice, it's just, you know, things like this, right? Because I have to constantly, I think I'm already doing better than the first day. Kind of force myself to not use any of the arrow keys. I think I'm doing much better. All right, so now here what we should have is num1, nums2 queries, and this is maximum. Oh, that's the thing. There's still sometimes you have to use the arrow key. Queries. All right, of course I do not want to do. Nah, I still forget this is a K. I do not want to take this. I can run this, and I have issue. Oh, dude. Ha. Nope. Not enough value to unpack. Num1, num2 query. Oh, I forgot to answer. Shoot. Yeah, answer is 6, 10, 7, 9, 9, 9, and -1. All right, let's see. Is it right? 0, 0, 0, 1, 2, 1 and 2, and 1, 2. Okay, so I have one question. I need to also do print max dot tree. All right, 1, 2, 3, 4, 5, 6, 7, 8. All right, I think it's good. Okay, so that's good. It does seem to be working. Maybe we do one more try. We'll query the entire thing. 0, 1, 2, 3. Okay, so I think it's good. Hold on. A7J. Okay, we'll delete everything. All right, so we have that. Next is we will have to sort nums1. We can put nums2 with it, right? I put nums2 with it. So what we're gonna do is xy, okay, equals to list zip nums1, nums2. I don't know. I mean, I haven't done this for a while, so I have to check. Yeah, this is right. And then we can, of course, also no, w, do sorted. All right. Okay, so we have sorted. Now what? This is xy. So now we have to have a stack. Right, a stack. So we have a stack. Okay. Then we go through each one of them for xy in xy. Yeah, maybe we can do, you know, this, delete this, of course. Can we paste this? Yes. And this one don't need any more. Go down. So for this x and y, if not stack, while stack and, so what do you put in the stack? Well, when you put in the stack an x, a y, and x plus y. Now, we just put x and y in the stack. Yeah, we just put x and y in the stack. But how do you know? Yeah, we put x, y in the stack, and if y is a bigger y will pop. Yeah, we don't care about x plus y, just a bigger y will pop. So while stack and y is larger or equal to, right? Larger or equal to stack minus 1, 1, stack dot pop. Right, so if my y is bigger, I always pop everybody. Right, if my y is smaller, I don't care about x plus y. So we do that, and then we say stack dot append xy. Okay, so let's see what the stack look like. I forgot some stuff. Yes. All right. So once we do that, now we're gonna say max seg tree is going to equal to is going to equal to max seg tree length stack. Okay, and then for height xy in enumerate stack max seg tree dot update. What's update? Index is I, value is x plus I. Okay, so that's also done. Now next we need to do binary search. Okay, binary search. So we have stack which looks like this. How do we binary search? I think bisect. Okay, hold on. How do we go to the top? We go up from bisect import. Let's go bisect left, bisect right. We might need both. And nope. Let's print bisect right, no, left. Okay, bisect left stack and 3 key equal to, hold on, this is we need Python bisect I have a key. Extract a comparison key from each element to support. So key equals to a lambda, I think. So key equals a lambda, a tuple, and tuple 0. 0, 1, 2. Yep, exactly. And we can also do, I don't know, and if it's too big, it's going to be on the right hand side. Oh, we have to do one more thing, right? If the query left and a query right, yeah. It's fine. Let's try a 5. Right? 0, 1, 2, 3, 4 on our side. Okay, so that's good. What we also want to do is so we're gonna do this negative. So the negative will be also increasing, right? So we'll give some value, and then is that bisect left or bisect right? We want to bias. It actually doesn't matter, right? I want to bias towards. So if it's in between, I have to go to the left, right? Because it has to be bigger. So, which means if it's equal to, I'll do this. Yes, it's still bisect left, but we actually have to check. Right, 9, 5, 4, 2. So if it's 3 minus 3, right? Minus 3 will be put into this position, so into minus 1. Okay, so still bisect left stack, you know, minus 3. So key to lambda tuple negative tuple 1. 0, 1, 2, 3. Yes. So which means we have to always minus 1. And if we do 4, it's be 0, 1, 2. 0, 1, 2. But in our case, oh, it should be bisect right because you want to minus 1, right? Because if you end, 3, you'll be ending it here, right? But we cannot end it here because this is smaller. We have to end at this, right? Because y is going left. And when you do this matching, you will push in here. So that's right. We have to go right. Yeah, that'll be 3. So we can, of course, let's see, this one, minus 1. Right? 0, 1, 2. And if we do 6, right? If we do 6, should be 0. There we go. Okay. So with that, what we're gonna do is, we don't need to print a stack. For query left, no, that's not query left. For QX, QY in queries. But of course, we have to also create an answer. Right, so this is the answer. All right, so for queries, query left, right, because X is going left, right? Query left shall equal to VI this. We will delete, okay, and then we'll go up and paste it, and then 5 become QX, okay. Query right will equal to Same thing, we go down, vi this, or delete, then we go up, and then we paste, and we find 6, we make it into qy. Okay, so now I have query left and query right. Then we say if query left is larger than query right, then rest.append -1. That's an impossible case. Else rest.append max_sec_tree.query query left, query right. Then we always have a solution. And then we return rest at the end. There we go. Let's go this. There we go. Let's go page up. We're gonna go from 37. Oh no. 90 milliseconds. Diane. Please pass. I passed. It freaking passed. So all the efforts was worth it. Ha. What should I say? I have nothing to say, but well, it was a Pista, right? It was a yep. Surprisingly, this solution passed on the first try. Of course, we did not solve it on our own. We use the hint. A lot. The idea is to first sort the xy. So first sort nums1 and nums2, aka x and y coordinates based on x, and then form a monotonic decreasing stack on y, right, on y. The remaining stack, right, is guaranteed to have increasing on x and decreasing on y, right? Then given a query qx and qy, we perform binary search on both, right? Binary search on both, which leads us to an index, an xi and a yi. So, right, since all the x's larger than qx are to the right of xi, and all the y's larger than qy are to the left of yi, then we the answer, right, the max x plus y must be the max of all x plus y in between xi and yi, right, on the stack. To solve that, to solve the problem of querying max value in a range, we use segment tree. That's it. We do on for this, on log n, so we have sort, and then query log n plus m log n. That's how I would do it. Okay, this is, wow. Map solution, segment tree, sorting the binary search, map. All right, we have to read. But I'm proud, okay? I'm very proud. This freaking works. All right, that will be it for today. I'll see you guys.